This is past year tutorial that I did as well. Before you can open it, please choose what you want to do with this SID. Hold on a sec. So I close this one. Okay, this is quite recent, right? Last year. Just go through. We are going through it. Don't worry about taking notes or anything. So this is a last year tutorial. Some of the work, right? Quite straightforward. So there are some calculation as well. Wow, I'm having a problem with this. Let's take a look at past year tutorials questions. This is exam questions, right? Past year exam questions. This one we are involving on the photochemistry, right? Basically, and a plot also involved, right? And how we do it, we're going to take a look at it later on. Okay. So I have past year exams. This is exam 2018. All right, 2018 exam questions. So last night I make it larger, make it full for this particular class. We take a look at the questions. Okay, let's take a look at the question. This is a chlorofluorocarbon. Right, it's considered right. The CH2 is considered for CFCs. Write this suitable equation when it reacts with hydroxyl radical that might occur in the troposphere. So the question is, you have CHFCl2, right? You have the CFC, right? Whereby you have, okay. If we take a look at what happened here, how we generate the hydroxyl radicals, okay. The first one, the 3, this is O3 is basically subscript O3. Okay. So this is I forgot. It is actually a Word document. Sorry about that. Okay. So it's O3, subscript 3. When we react with the UV, light energy, okay. So you have O2, right, split into O2, oxygens, and you have oxygen radical. This is radical, right? This is radical. And then the radical of oxygen will react with the moisture in the air, okay, to form the OH radical. All right. Anybody coming? Just let me know. Can you see the? Can you see my slide?
Yes.
Okay, good. Because I'm just using one computer here, one tablet here. I'm not using any other gadget. So only one. So I don't see what's on the screen. Okay. So this is how we generate the OH radical. So the question is reducible equation when it react with hydroxyl radical. So you can imagine is how you actually you have OH. So this one actually not necessary to write on OH radicals for today purposes. I explain a little bit on what happens in this troposphere and the hydroxyl generations. This is the radicals generations. So how we come about with OH radicals? It start from ozones, then the oxy radical react with the water to form the OH. So you see the stoichiometry. O is radical, single oxygens, right? Water H2O, one water molecule. So two hydrogen here, one oxygen. So you have two OH. Now, what responsible with OH? Okay, you can write there's several maybe different reactions with the OH. So it is basically you talking about CHF Okay, you are given CHF I just mark here. Right, you are given this, and it react with hydroxyl. Okay, it react with OH. Yeah, with OH. And this is just one example because the question is write a suitable equation. The suitable equation when it react with hydroxyl. So you may have several other because this is open reaction. The radical is not specific, and the CHFCl2, right? One of the reactions actually kicking out the hydrogens. So OH plus we react with the H. Okay, we react with the H. So I wrote in this manner so that we can see that we focus on that particular reactions and giving you water molecule and one electron, right? So the H here you can kick out. So you have CFCl2. This is a radical, okay? This is a radical form, right? This is the radical form, which is open for the next reactions, right? This is the first reaction can take place. You can also react with the chlorines, right? Because chlorine also a good leaving group. Okay. The second question, this is with regard to the luminol, which is straight from your lecture notes. Okay. The second questions, this one is 6 marks. The first one was, excuse me, 5 marks. So this is very short questions, but normally if you don't see the answers, it's very difficult for you to answer, right? If you don't see the answer, it'll be difficult for you to, okay, which one to write and so on. Now you've seen the answers, so it will look easy. Okay, that's why given 5 marks, right? The second questions is 6 marks. So again, since it is from your lecture notes, right? Asking you oxidation of luminol is example of chemiluminescence. How does this process different from bioluminescence? Now, the question actually asking you chemiluminescence and bioluminescence. Okay, the question actually asking you the chemiluminescence and bioluminescence, right? So it using preambles, not on luminol, just to highlight a little bit the chemiluminescence. Okay, highlight a little bit of chemiluminescence. Okay. And the answers should actually describing the difference between chemiluminescence and bioluminescence. All right. So the chemiluminescence, okay, you can write as much as you could. Okay. Remember, there's a 6 marks there. If you divide 3 each, so you need a 3 points from each, right? You can write the 3 points. You can write the differences, or you can write in one sentence, but describing what's the difference. Chemiluminescence, what is it? Bioluminescence, what is it? All right. Chemical reaction, very simple, biochemical, biological, living things. You can write a lot of things. Huh? So, yeah, many choices here to write, right? Many options, right? But if you write 3 each, one chemiluminescence, the difference to bioluminescence, and one bioluminescence, the different to chemiluminescence, or you write one sentence that describing the 2 differences, okay? But again, that is a bit limited. If you write each, the difference that different from bioluminescence, right? That is much better, okay? So I gave you example here. No excitation source. This is straight from lecture note, but you can write, other things as well, okay? Okay, does not produce heat and so on. Okay, you can write those, right? So I just give you example: no excitation, single light detection, no monochromator, right? You can write all those, right? For bioluminescence, this is one actually only by living organism. Okay. So both actually converting into light emissions, right? Bioluminescence actually, that's another I mentioned just now. Does not evolve heat, so because that's going to harm the living cell or living organism. Okay, you can write those as in lecture notes, plus in addition to what discussed in our lectures. Okay, so I'm just giving you an example here, right? Some of the questions, but don't write on luminol reactions because it's going to waste your time. Yeah, only waste your time. Okay. Remember, you have other topic from different lecturers, different part of question that you have to answer. So go straight to the difference between chemiluminescence and bioluminescence. That was the questions. So I just put here some example here just for this particular purposes, our lecture notes. So the answers is straight. Do not write the equations. Okay. So just to recap it, on luminol. So this I just put last semester, last year. I put this in part of our tutorial comes recap the topic that's related to the exam questions. Okay, we get to the next questions. Okay, remember this is on the photosynthesis, so there are different. We have the first questions actually related to the first lecture notes. Okay, this is bioluminescence, then This one actually related to photosynthesis, right? Related to photosynthesis. Right. The questions you are given some constant, right? So you don't have to actually look up all these constant from the table of constant books given to you. So normally I give all the constants so that it's easier for you to use those constants in your calculation. All right. Okay. The first question, right? Photochemical reaction between heme molecule and chlorophyll. So in 2018, I don't know, a lot of students actually cannot write these equations, right? Because they cannot remember the polypyrols with the magnesiums molecule. I'm not asking you to write the whole molecular structure, right? You are given here, right? Heme molecule. You can actually write heme, right? Here, HEME. Okay, representing the molecule. You don't have to draw the chlorophyll molecule, right? Or the other molecular structure, molecular formula. You don't draw this. Don't write the molecular formula, right? I also cannot remember. I'm not that smart to remember the whole molecular formula of hemes or chlorophyll. Okay, so it takes time for me to write the whole molecular formula. So do not do that. So like chlorophyll, you just like CHLO, for instance. So heme molecule, you just write HEME, right? And then you draw the whole molecular structure. That was the first question. This photochemical reaction, right, involve light. Okay, that's involve light. So somehow you have to put H mu, or you can write light, right? It doesn't matter. That's representative reaction. But normally we write H mu, isn't it? Right? So next, in a photo-induced electron transfer reaction of acridine orange, predicted that spectral centered at 425 nanometer and 540 nanometer. 425 and 540 nanometer, corresponding to the emission from the first excited state and triplet state, respectively. Okay. The questions: calculate these energies in the form of electron volts and draw the corresponding Jablonski diagram. Remember, right? Converting into EV. So of course you need the 1 EV 1.6 charge, times 10 to the minus 19 joules. Okay. Right. And forget about acridine orange here. It is a dye molecule. Okay. Don't freak out. Like how do I know the acridine orange molecule? So you don't know, right? Because the question here is not actually asking you to draw the acridine orange molecular structure or molecular formula. Okay. Focus the question asking you, all right, to convert this energy into electron volts, all right, electron volts. Okay, that is the question. And then the second one is Jablonski. So you only have two data here, right? The fluorescent energy, which is first excited state, and then you have phosphorescent energy. Okay. So first excited state is fluorescent. Okay. The triplet excited state is phosphorescent. Okay. So you have two hints here. One is phosphorescent, second is fluorescent, the other one is phosphorescent, and you are given the emission energy. Right? So this is how I do for the first questions. You use heme, right? Remember, the electron actually transferred from the heme molecule to the chlorophyll in photosynthesis, right? Heme's actually the sensitizer, the one which is actually absorb the lights and immediately transferred to the chlorophyll because heme sitting outside, right? So heme plus H mu should have excited heme molecule. So if you don't have hemes here in normal photochemical reactions, okay, if a molecule, if a substance is exposed to UV radiation, let's say sensitizer or dye, put D or S, react with the light energy that exposed to it, it'll get excited. So once you get excited, typically we get the superscript, okay? This is superscript star. All right, superscript star. So write that. That indicate they are actually in the excited state. Okay. So the hemes, right? They have the chlorophyll, okay, and you can write CHLO, CHL, so it doesn't matter. But okay, so you have the transfer to the chlorophyll, and the chlorophyll become excited. Okay. And the second part of the questions, okay, all these Planck constant, all the constant actually given. So remember that simple equations, right? The simple equation. Okay, you have lambda, the two wavelength at the moment. You have the Planck constant. You have speed of light. Okay, you write them down. Okay? Don't forget, write them down in your answer sheet. Okay, write the equation down. Okay, write the equation down. Write the constant down as well. You know, sometimes, and I wonder if some students they know how to write the equations, but when they plug in the numbers, now they put in the wrong number. So just a simple habit that you should have, write them down. Okay, this might cause a simple mistake. I don't know, when you are in a hurry, right? You have to answer the next question, and you are thinking about, oh, I haven't done this, I haven't done that, I have to do this, I have to do that. So you tend to make this silly mistake. Then instead of you write a Planck constant, you write, put a different value there, right? You write charge, for instance, okay, and so on. So you don't write a Planck constant. This is the numbers of Planck constant. I think you memorize them. It's much better. Okay, memorize the Planck constant number 6.626 times 10 to the minus 34 seconds. Right? Just like the electron charge, 1.6 times 10 minus 19 joules. Right? Just like gas constant, just like all this Boltzmann constant, right? Because they are interrelated. Avogadro number, those are simple constant that you can memorize them, right? You remember it forever. Okay, especially if you look at gas constant and Boltzmann constant, they are related, isn't it? There are only three of them: Boltzmann constant, Avogadro number, and gas constant. So you can get them. All right. So anyway, the question asking you electron volt, right? The question asking you electron volt. So you go back to the questions. Another silly mistake that the student did was, right? I don't know why the student forget about converting into EV voltage, electron volts, right? They only see Jablonski diagrams, then they saw these numbers, wavelengths, right? And just plug in the numbers wavelength into Jablonski diagram. Well, you are first actually find it out in electron volts. Okay, got that? So in my case, because you have the HC, right? You write it. I write every unit along unit next to it. So joules meter joules, right? So 1 EV equal to 1.6 times 10 to the minus 19 joules, 1 EV. Okay. So in what I get here, right? What I get here is in EV meter. Okay. If you are given EV, if you are given EV, you want to find out the wavelength in nanometer, right? Just in case the EV, how you get the EV? You get the EV from, for instance, cyclic photometry. For instance, the cyclic photometry can give you the fluorescent energy, right? The fluorescent energy. Fluorescent energy, where it fluoresces, it gives you the cyclic photometry. The same, right? Cyclic photometry in the form of EV. So if you are asked, right? If you are asked to write in nanometer from cyclic photometry analysis, right? From cyclic photometry analysis, which means you have to convert into nanometer because cyclic photometry giving you EV. There's no nanometer, no wavelength, right? It's a electrochemistry technique. So you just multiply, because you have one EV, right? I just put there an electron volt, one energy required to raise one electron through volts with energy 1 EV. So remember your 1 EV, right? And then you have to convert it into 1.6 times 10 to the minus 19. This one in joules units, right? So how many EV you get? 0.3, so you multiply. You get 0.4, you have to multiply. You get 1.5, then you have to multiply with the 1.6 times 10 to the minus 19. Okay. So this is how this is, I mean, vice versa, right? Vice versa, right? So once you calculate all the value, right? Once you calculate all the value, you can use your own way so long as you get the right number. Okay, like myself, I just calculate in the HC first, converting to EV. So you can do whatever you like to convert into EV, right? You can multiply and divide to get the EV value. So in this case, you have 296 EV, Jablonski diagram. And you have this and you convert into Jablonski diagram, for instance. right? So hang on a sec. This is wrong. Sorry to say. Right? Let go. I compare this one wrong. It's not right. Okay. Okay. The first one. Okay, I wrote this. Okay. Forget about this. Forget about this number. Let's see whether I can. Yes. It's not. It's not. I can edit this. So this is fluorescent. Hang on. Let's change it. Okay, this one. The 287, 2.87 actually over here. Right? Let me see. Oh. Oops. Okay. Now, I can write 400. Let's say 400. Okay. This is hypothetical energy, right? Excitations. Okay. 400 excitations and realizations. Okay. Go to the ground state. Okay. Your first emissions is the fluorescent. Fluorescent is first excited state. Right? The phosphorescence should be right behind this crossing to the triplet state. So the triplet state energy should be lower somewhere around here, lower than S1 excited state. Okay, and then the energy actually coming down. I cannot draw on this. Let's see. Oops, it's not there. Uh-oh. Okay, guys, can you hear me? There you go. Yeah. Okay, good. Sorry, what I'm trying to do is I just pick up. Just pick up one blank somewhere. Okay. So I can draw in here. Right. Oops. Okay. You have a ground state. You have the excited state. You have the triplet state. So this one is triplet state. You can do that. You can do that. In order, you must have the excitation, right? The molecule must actually absorb higher energy. So these excitations, of course, you need energy pump in, light energy being pumped in. And the first with lambda here, right, hypothetically lower than 425 just now, right? Has to be, because it has to go up to the excited vibrational state. Okay, you have to go up here, and you don't undergo relaxations. Okay, the fluorescent energy is this one here. Okay, so this is giving off fluorescence. Okay, giving off fluorescence. We need in EV energy, right? So this one is 418. So you have 218, right? This is 425 and 540. Okay, I just put 425 and 218 and 2.87. Hold on a sec, where is it? Oops. Okay. And after you come down, right, there's an intersystem crossing over here. Okay. And we relax to the lowest excited triplet state. Now, as it comes down, this is actually EV for your phosphorescence. Okay, EV energy. So you have the two emissions, right, in your answers. So put the value here, right? Okay. So this then is complete Jablonski diagram. Right? Okay. Put those two values in the Jablonski diagram. So it must be complete. Right? It must be complete, as I drawn just now. Okay, forget this. Right? Any questions? You taking notes? Okay, guys. If not, no questions. Because I have right, I need to prepare for my class. Or I have about 10 minutes or so to prepare for my laboratory class. Okay, guys. Thank you very much. Don't forget your attendance in our Google form.